Hello, it's Scott Manley here. Back in November of 2022, a small jet plane departing from Indianapolis crashed soon after takeoff. Now, thankfully, nobody was injured, and a big reason for the safe outcome was that this jet was equipped with an airframe parachute that could be deployed by the pilot to land a stricken aircraft safely. So the aircraft touched down on the shores of a canal or a pond, and soon after there were all sorts of social media stories highlighting this amazing event and explaining how the innovative parachute technology, the first in a certified jet plane, saved the day and the pilot's life. Now, 2 years on, we have the NTSB report, and it looks like the parachute system was partially to blame for the crash. And this represents a perfect opportunity to discuss the technology behind airframe parachutes. Now, if you've played Kerbal Space Program and built aircraft, a lot of you out there have probably, instead of putting landing gear on your aircraft, you put a parachute on there, because that's much more reliable in terms of getting you to the surface. It turns out that modeling the aerodynamics of an aircraft is a piece of cake compared to modeling the interactions between wheels and the ground. And it's quite common for your aircraft to bounce around and go crazy, hence parachutes being used. But Kerbal Space Program is not a reflection on reality, and most aircraft land on wheels. Designing a parachute system that can fit onto an aircraft to save the entire structure is a big engineering challenge. Now, the company behind this technology is Ballistic Recovery Systems, BRS Aerospace, and they were founded in 1980. Their founder, Boris Popov, had an accident in 1975 where a hang glider partially collapsed and he fell to the ground several hundred feet. He survived that and decided that they needed a way to save small aircraft like that. So the first product was launched in 1980, and their first save was in 1983. Initially, this was for ultralight aircraft, fabric wing framed structures. But in the 90s, they began to extend upwards to heavier aircraft. They got grants from NASA to develop this technology. They started fitting them in Cessna 150s. And these days, you can buy retrofit packages for Cessna 170s, the Cessna 180s. But their most important collaboration was with Cirrus Design in 1998. And Cirrus are the designers and builders of that jet that I mentioned earlier, but their first product was the SR-20. This was a modern, all-composite, low-wing, propeller plane. It was fast, it was awesome, and every single one of them would come with a parachute system built in, the Cirrus Airframe Parachute System, or CAPS. And that was a massive selling point to a lot of potential pilots. Of course, there were a lot of older pilots, perhaps, more skeptical, who said, if your plane suffers an engine failure, you should know how to land it in a field. And I would counter with the observation that there's many other ways that aircraft fail beyond losing engine power, some of which do not leave the aircraft in any controllable state. There is actually an interesting consequence that sort of affects basic airmanship in the Cirrus, and that is that when they certified the aircraft, they claimed that because they had a parachute, they shouldn't need to demonstrate spin recovery. And so the manual, the pilot's operating handbook, has a checklist item that says if you're in a spin, you deploy the parachute system. And that's led to a bunch of people saying that the Cirrus can't recover from spins and therefore isn't a real aircraft. But the truth is that when they tried to certify the aircraft in Europe, their parachute argument didn't work and they had to actually go up and demonstrate spin recovery, and it did it just fine. But I will say it is kind of frustrating that the official manual says that you will deploy the CAP system rather than, say, putting in the correct rudder inputs and cancelling the spin. The fact is that after 25 years, it's saved a number of lives, and it's also helped Cirrus sell aircraft. I own a small aircraft, a two-seater called a WT-9 Dynamic, and I've had this for over a year, and my wife has never flown with me in that because it doesn't have a parachute. Instead, she'll only fly with me in the Cirrus, which I have to rent, which costs about 7 times as much per hour. And that is why it is currently getting a parachute system fitted right now. So anyway, Cirrus made a point of putting parachutes in all of their aircraft. The first one was the SR-20, and then there was an upgraded version called the SR-22 and the SR-22T turbo version. And when they introduced a jet, they wanted to figure out how to put a parachute on that. And as you can imagine, there's a lot of engineering challenges. A fully loaded Cirrus SR series aircraft would weigh about 1.5 tons. So you need a parachute that is capable of handling that amount of load. Then you need to be able to secure it to the frame in a number of places so it won't detach. You then need a deployment mechanism which will make sure it doesn't create transient loads which could cause it to break apart. And then, of course, you have to make sure it deploys in a manner which doesn't tear the parachute apart. And aircraft move faster than your typical skydivers. And then, of course, you need a deployment mechanism that will make sure the canopy is clear of the airframe so it doesn't get entangled in it and render itself useless. And one of the ways they do this is with rockets. So yeah, that brings me a certain amount of pride to say that one of the aircraft I fly actually has a rocket built in. So on the Cirrus, there's a red T-handle in the roof of the cockpit. There's a pin you have to remove prior to taking off. But yeah, you'll pull this down and then pull the handle hard, and there's a cord which is connected to a rocket in the back of the plane. So pulling on the handle pulls back a plunger, and if the plunger comes back far enough, it slides in and hits a pair of contacts which will energize the rocket ignition system. This is of course wired into every battery and you can never disconnect it. The rocket motor is a small solid rocket system, and the igniter is a small gas generator at the top which blows hot gases down the middle and ignites the rocket in a fraction of a second. And if you follow my channel, this kind of stuff is familiar territory to you. So now that rocket blows itself up through the back of the aircraft, knocking out a panel that's in the structure, and as it flies away, it's actually attached to the bag around the parachute, so that when it reaches full length, it's going to pull the bag off. But before it does that, there's this incremental bridle structure, which has a whole bunch of loosely sewn folds into the cord, so that it actually, the stitching comes out slowly and therefore reduces the jerk, right? Which is the technical term for the derivative of acceleration. A massive jerk could easily damage the parachute. So anyway, as the bag gets pulled off, the parachute will begin to unfurl. And the problem is now, you don't want it to unfurl too quickly because that will again apply a massive jerk to the aircraft and potentially break things. So this parachute includes a ring which is attached to all of the suspension lines on the parachute, and it constrains the amount by which the parachute can open. And then as this ring slides down these lines, the parachute incrementally opens and therefore decelerates this aircraft, but not so quickly that it potentially exceeds the structural limits of the airframe. The parachute is anchored to the airframe by multiple lines, and these lines are actually embedded underneath the skin of the aircraft, and as this parachute deploys, they pull out and tear the skin, but they distribute the load over the aircraft. Now, to stop the aircraft pitching up when they deploy it, it's connected in such a way that the sort of center of connection is further back in the aircraft, which, again, reduces the pitch up, but the problem then is that you're nose down, so they have a reef cutting system where that connector at the back has a timed guillotine which will kick in about, I think, 10 seconds after deployment, and that will make the aircraft drop its tail and land a little more level so that it lands on its wheels rather than landing nose first. And so over the last 25 years, there have been over 150 uses of this system, and about 130 have been successful. And the two most important factors in a safe CAPS deployment are deploying it with sufficient altitude, which is about 500 feet or above. And in fact, that's so ingrained into the pilots that when we are taking off out of the airfield and we pass 500 feet, we call out CAPS available. And the second critical parameter for parachute deployment is speed. The maximum safe parachute deployment speed is 133 knots. Above that, there's more and more chance that the parachute is going to tear off and not function. And there's a couple of well-known cases where an aircraft picks up ice in the clouds and starts descending, going faster and faster, and by the time the pilot pulls the CAPS system, the aircraft was going too fast and the parachute just tears off. And so That sounds like a pretty horrible situation to be in. But if you get into an emergency situation and you deploy the parachute at above 2,000 feet and below a speed of 133 knots, the chances of you walking away are really high. The system has saved the lives of hundreds of people and even a few dogs apparently. One of the most spectacular saves was a ferry pilot who was moving an aircraft from California to Hawaii, and because they had to cross so much ocean, they had an extra fuel tank inside the cabin, and while they're about halfway across, they're unable to transfer the fuel into the main tanks, and so he understands that he's only got a few hours worth of fuel and he can't make it to Hawaii. He's able to radio in, they get Coast Guard helicopters out, they direct him towards a cruise ship, and then once the fuel runs out, he pulls the parachute system and descends into the water. So we have recordings of this from the Coast Guard. We have him recording the experience from inside the aircraft. And there's quite a few photos from the cruise ship as well. And, you just wouldn't want to be ditching an aircraft like that on the water with fixed gear because it had a high probability of flipping over and it would be very hard to escape from in that situation. So when Cirrus wanted to take their aircraft offering to the next level and develop a jet, they knew that this had to be part of the system, even although the jet was going to be almost twice the weight of the propeller-driven aircraft. Development on what would become the SF-50 Vision Jet began in 2003 and it was announced in 2006. They started taking deposits. There was a bit of issue with the recession, bankruptcy, but eventually they started delivering them in 2016. And since then, it has been basically the best-selling business jet in the world. And it's pretty compact with a wingspan that's only slightly bigger than the prop-driven Cirrus. The jet in the Cirrus jet is a Williams J33-5A that provides about 850 kilograms of thrust. And you can see it mounted in the dorsal section just behind the cockpit there. The location of the jet means they can't use a standard vertical tail, so they have to use a V-tail. And that in turn forced them to find a new location for the parachute because that's where it was in the SR series. So the parachute for the Vision jet is actually in the nose in front of the pilot. Then because the jet is almost twice the weight of the prop version, they need a much bigger parachute, and that needs a bigger, more powerful deployment system. And they realized that they couldn't quite get away with just putting a bigger rocket in there. They actually had to develop a new deployment system, which was like a combination of an airbag, like on a car, which was designed to push the parachute package out of the aircraft, and then the rocket would activate and complete the parachute deployment. And this is some footage from an actual deployment test with a test pilot in the aircraft. So you can see the parachute getting pulled out and beginning its deployment and slowly expanding. What you can't see here is after the camera cuts away, the test pilot actually just cuts the chute and the aircraft then actually flies away. But these tests were obviously enough to convince the FAA, and it's in basically every Vision jet you buy. Or at least in every Vision jet that's sold. I mean, I can't afford this kind of money, but if somebody out there has a jet, I would love to go flying. So anyway, the first time this system was used in a real aircraft was in 2022. A pilot was performing an instrument approach in Florida, and the approach path took him through some really bad weather, which was beyond his pilot skills. He was unable to maintain control of the aircraft, and eventually gave up and pulled the cap system. It deployed the parachute and successfully they descended into a swamp and all three occupants survived. But the second time it was used, well, that was the one departing Indianapolis. In this case, the pilot took off and moments after takeoff, he activates the autopilot to hold his pitch and get the correct climb in. And moments later, the autopilot starts slowing the aircraft down, pulling the power out and pitching the nose up, which is a very dangerous situation to be in. So he immediately starts counteracting the autopilot, putting the power back in and putting the nose down. But every time he lets go of the throttle, it's pulling the throttle back. He's pushing the red button, the disconnect autopilot button, and it's not working. And so after fighting the aircraft for a short time, he eventually pulls the caps and descends the aircraft safely, but that's the end of its flying life. So what was going on? Why was the aircraft behaving so strangely? Well, this comes back to the discussion of parachute deployment speed. If you remember, 133 knots. And one of the reasons to own a jet plane is because you want to go a fair bit faster than that. And so during the majority of the flight, the aircraft is going too fast to safely deploy that parachute. So their solution was to integrate the parachute deployment process with the autopilot. So if you pull that red T handle, it's no longer a physical connection to the rocket motor. It activates a sequencing system, and the first thing it does is it tells the autopilot that CAPS has been activated and the aircraft needs to slow down. So the autopilot will do this by pitching its nose up and pulling the power back. And that's exactly what the autopilot thought it was supposed to be doing. But it's a special autopilot mode that can't simply be cancelled by the autopilot disconnect button because it's so important to the safety of the aircraft. When you push the autopilot disconnect, it'll temporarily disconnect the stuff while you hold the button down. But to disable the mode completely, you have to hold the button for 5 seconds. And this is supposed to be a memory item in your checklist. That means if you see these particular conditions, you're supposed to know without looking at the checklist that you have to hold the autopilot disconnect for 5 seconds. So in this case, the aircraft had been transitioned into this CAPS deployment mode, even although the handle had not been pulled and the system wasn't actually going to deploy the parachute. But the pilot didn't recognize that he needed to hold the button for 5 seconds to cancel it, and so he eventually gave up. Now, to be fair, I had an autopilot anomaly recently, and it took me a good few seconds to figure out what was going on, and I was flying on instruments. I was supposed to be looking at the display in front of me. But I'd never seen a failure like this before, so I wasn't quite sure what to do or how to interpret it. And incidentally, this is the 7th generation SR-20, and the big feature that they introduced was that the avionics, the panels, were copied from the Vision Jet. Anyway, initially the investigation didn't know that this was what had caused the problem, but they were investigating the hardware, they pulled everything apart. One thing that they found was the control box that coordinates all this had shown some signs of corrosion as a result of water intrusion into the system. So there were 2 pieces of electronics that they pulled from the aircraft and put in a lab. One was the CAPS control board, the one that would be doing the actual logic, but the other, which showed the corrosion, was what we called the primary power holdover timer card. And this is essentially an uninterruptible power supply. This would ensure that even if there was a complete electrical failure on the aircraft, that CAPS would still have an independent power supply that was good for at least an hour. The control box worked fine when it had continuous power supply, but given that the power supply was corroded, they wondered what would happen if there was momentary glitches in the power supply. So you basically turned the power on and off very quickly, and they found that when that happened, the controller would send the signal that CAPS had been activated. So it's believed that there was some sort of disruption in the electrical power supply. Possibly when the gear is retracted, that's electrical, so it increases the load on the system, causing enough of a glitch in the power that the CAPS control box assembly thinks that the handle has been pulled and begins to initiate the CAPS slowdown sequence. And so to ensure this kind of thing didn't happen again, they modified the hardware. The control assembly had new hardware to make sure that momentary glitches wouldn't set off the signal. And the power supply, the timer or whatever, it was potted to make sure that water couldn't intrude and start causing issues. Anyway, zooming back out, the parachute systems, they're not exclusive to Cirrus. They're now available for a lot of aircraft. In particular, there are a lot of light sport aircraft that have this capability. And I think this is partly because a lot of these aircraft are relatively new and therefore they were developed after the advent of this technology. But the Cirrus jet has one other innovative safety feature, which it was basically exclusive to this aircraft for a long time. Now, you might remember a couple of months ago I made a video about a woman who had to land a King Air twin turboprop after her husband, who was a pilot, died. She had very little aviation experience, and yet they were able to talk her down and she was able to bring this monster airplane in for landing. And you might think that if the aircraft had a parachute system, that would have made things a whole lot easier. She could have just popped the chute and landed it, and that's absolutely true in the Cirrus SR-20 and 22. But the jet has a completely different feature which is even more useful. The second generation Cirrus jet was the first small jet to be equipped with Garmin's Autoland technology, or as Cirrus calls it, safe return. And the way this works is there's a big red button that if you push it, it will start the autopilot towards landing at the nearest convenient airport. This is entirely implemented using GPS for navigation. It doesn't need any instrument landing system or anything. When activated, the aircraft will use its database to find an appropriate airport to land at. It will navigate there and it will make some automated calls over the radio to tell everybody that it is operating under autopilot and it's going to be landing. Now, I haven't heard any stories about this actually being used, but it obviously is an amazing feature. In fact, it won the Robert Collier Trophy back in 2020. This is an award that's won by things like the X-37B and the Parker Solar Probe. It is truly, top tier aeronautics. But as of right now, I think the Cirrus jet is the only aircraft which has both Autoland and an airframe parachute, giving the passengers twice as many options should something go wrong. So I hope you've found this whole thing kind of interesting. This is a really fascinating piece of technology, and it's something that I have to know all about because I fly with it. But equally, it's hopefully something that I never actually have to use myself. Indeed, rocket-powered airframe parachutes are a piece of technology that helps me, Scott Manley, fly safe.